Alright, this project served to investigate human reaction times. A little background. Reaction times vary among individuals greatly, and this project served to investigate the reaction times of 20 different human subjects. This was done by gathering reaction times of each subject 10 times, and then using these reaction times to plug into Excel to generate the mean and standard deviation. This resulted in over 200 separate reaction times being recorded. In order to record these reaction times, an RT strip was made out of cordstock with evenly spaced 5 mm distances. To calculate the time for each corresponding distance, the kinematic equation y equals 1/2 times acceleration times time squared was used. Then, algebraic manipulation was utilized and plugged into Excel, and that allowed me to quickly and accurately determine the time for each corresponding distance on the reaction time strip. Here is an example of a distance versus reaction time graph for a known specified time periods. With known specified time increments, a graph was generated to reflect the corresponding distances in millimeters using the kinematic equation shown in the previous slide, y final equals 1/2 times acceleration t squared. This graph is also an example of a distance versus reaction time, but this time it's for known specified distances. As you can see, the line itself is almost opposite to the other one. With known equal distance increments and the kinematic equation that we also used in the previous graph, we can figure out corresponding times. This graph is a reflection of what my card strip shows as well. Now, the three equations that we used in this project were number one, the kinematic equation I previously described. This allowed me to determine the corresponding times for each 5 mm distance as we went up from 5 to 10 to 15, etc. All the way up for me until about 210. The second equation that we used was the mean. This was calculated using Excel, and what I did was I took the data from every trial, which was over 200 different entries, and then I plugged it into a cell that automatically calculated the average for me. The average reaction time for my experiment was 160.5 milliseconds. Lastly, the third equation that I used was the standard deviation for the reaction times, again using Excel. The standard deviation is a measurement of the dispersion from the mean. This was determined using an equation in Excel, which I plugged in all the entries into that equation, and it spit out a result of 30.53 milliseconds as my standard deviation. This is a pictorial representation of what my Excel sheet looks like with the equations that I used. As you can see, the first one is time, and this is the algebraic manipulation that allows us to just plug in our final position and our acceleration and calculate time right there, which is the square root of 2 times the final position divided by the acceleration. Next was the calculating the mean, which is just the average, which is the sum of all the times divided by how many different trials I did, which was 200. And that was 160.5, as you recall. Lastly was the standard deviation. This equation is a little bit trickier, but essentially it's the square root of the sum of a particular time minus the average squared over the number of different trials minus 1. And that was used in Excel, and that spit out an answer of 30.5, I believe. Here is an example of my results. So as you can see to the left, this is a section from my Excel. It's a little blurry, but this is a section from my Excel spreadsheet that shows on the left is person 1, next in the red is distance, and then I have all distances below that. To the right of that in blue are the reaction times, which were calculated using the distances. The results showed a mean reaction time of 160.505 milliseconds, with a standard deviation from that of 30.53. Alright, on to the questions. So, on Moon, the gravity is around 1.62 meters per second squared. This obviously is a lot lower than the gravity on Earth. Therefore, the RT strip will fall much more slowly. We would need to create an RT strip with smaller distance increments to allow for accurate time measurements to be made. And if you plug in numbers into the kinematic equation that we've already talked about, you'll see that this makes sense. The vertical distance for the RT strip per unit time is much less than on Earth because of this decreased gravity. In contrast, on Jupiter, which has a gravitational acceleration of 25.9 meters per second squared, almost 3 times that of Earth, the RT strip is going to fall almost 3 times as fast. Thus, the RT strip distances would need to be spaced further apart to allow for that increased drop time. All right, on to question 7. So, if an elevator is traveling up at a constant speed of 10 meters per second, this means the acceleration up is 0. Thus, the only acceleration acting on my card strip, or my RT strip, would be gravity, which is the same as if I were standing in the elevator and I dropped it, it would free fall, because gravity is the only acceleration acting on it. And thus, it would be no different than if I was standing in the lab, doing the same thing. For B, the answer is essentially the same. Even though you're traveling in the opposite direction, you're still traveling at a constant velocity downwards, which means your only acceleration, again, is going to be gravity, pulling it down. And thus your card strip will drop as if it were in free fall. So now C is a little different. If the elevator is accelerating upwards at 10 meters per second squared, the RT strip will fall with twice the speed